All right, I'm back, and now we want to do the inclined plane. And so a inclined plane is going to have a certain height, which we're going to call the rise. And then it's also going to have a certain length. So don't mistake it for this distance over to here. So it's not the run, okay? It's going to be the length. So the length L is going to be this distance right here. Now you're going to have a box. And so here is going to be a box down here. And your goal is to push on the box with a force in. And then what it's going to do is you're going to push the box up to the top of the ramp. Now you could have, so let's put it over here, you could have taken the box and lifted it directly up. So this box has a weight that pulls straight down. And so this is going to be the force out. So that's going to be the weight of the box, and gravity pulls it straight down. And you could have lifted it straight up. So grab the box, lift it straight up this way. Okay, now let's look at the amount of work it would take. Work is going to be force times distance. If you lift it straight up into the air, you're going to have to apply the full amount of the force. So the full amount, the full weight of the box, you would have to apply it. And you'd have to lift it this distance right here. But look at the other way of doing it. Do you notice that the length is larger than the rise? So instead of this, let's put in a large L, and then over here, let's put in a small rise. So the length L is larger than what the rise is. So what does that mean? So that means that this is going to be compensated by a big F, and then this side over here is compensated by a little f. So you're going to apply a small amount of force in, but you have to push it through a large distance. But the good news is it's a small amount of force compared to the weight of the box over there. So this is how an inclined plane is going to work. So let's try one. So a person can only push with 30 newtons of force, but they need to lift a 100 Newton box to a height of 1.5 meters onto a loading dock. How long of a board do they need to have in order to accomplish this? So the loading dock here is going to be 1.5 meters up. So that's going to be the rise. We don't know what the L is. We do know what the box was. So the box is 100 newtons straight down. We know that we can only push with 30 newtons. So that's going to be this. So we're going to plug into this formula. 30 times the length of the ramp has to equal 100 times 1.5. So the minimum length of the ramp is going to be 5 meters. Now, you could make the ramp longer. So if you make the length of the ramp, let's say 10 meters, can you figure out how much force that you're going to need to apply? Only 15. So the longer that you make your ramp, the less force that you're going to need to apply in order to get the box to go up there. So now you're saying to yourself, well, that means if I had a ramp that was 100 meters long, well, then it would hardly take any force to move it up there. That's true, but that's a lot of walking. So the longer you make your ramp, the further you're going to have to walk and push that object up there. So there is a limit to how long that you can make your ramp. And then the other thing is we're assuming that this is a perfect ramp, which means all the energy that you put in is going towards lifting that thing. But you should know that the box, when it rubs against the ramp, that's going to be friction, and so that's going to produce heat. So the longer your ramp is, the more heat you're going to generate, and the more energy is going to be wasted when you do this. This has a really practical application. I'm going to give you two historical applications to this. So the first one is the Great Pyramids. So have you ever wondered how did they get, so let's say that they're building their Great Pyramid, and so they've got this much of it done, but they need to get more blocks up to here. So how did they do it? Well, it's been speculated that what they've done is they took sand and they piled it up against the Great Pyramid like that, and now you've got a what? A ramp. So then they could take those blocks, and they would also wet down the sand to make it less friction. And so then, and they've also been speculated they use rollers in order to do it. And so then they could drag these big blocks up to here, and then when they got completely finished with the pyramid, then they would just get rid of all that sand. Pretty cool, huh? Okay, another application of this is Masada. So in AD 64, something like that, the Jews in Israel revolted against Rome. And so the Jews lost, and so the last hideout that they had was Masada. And so Masada was this great rock off the coast of the Dead Sea, and you can see down there at the bottom, it tells you how tall Masada was. And then on top of it, it was actually a palace that was built by King Herod, but it was actually a fortress up here. So it was very well defended, and it was almost next to impossible to get troops up here in order to attack the buildings that were on top of it. So what did the Romans do? Well, the first thing the Romans did was they built a wall completely around this mountain, psychological warfare, so that the Jews would see this and realize how hopeless their situation was. But as soon as they completed that wall, the next thing that they started to do was they started to build a ramp up to the top of it. And then they could take their siege engines and roll them up the ramp and then start to batter down the walls. But the story goes that once they got all the way up there and they battered down the walls, they found that everybody was dead. So that instead of being taken as slaves, the Jews up there decided to commit suicide. So in this picture here, you can see the ramp. So that ramp that the Romans made is still there today. Okay, so that's an application of a simple machine. Okay, let's take a break. When we come back, we will talk about the wedge and how it is a simple machine.